Okay, welcome to part 2 of your Kin 425 class. Just a quick recap. From the previous section, the last question I asked you which proteins were increased in that fat metabolism diagram. One protein that I forgot to mention was that your fatty acid translocase. It's that transport protein that allows fats to get into the muscle fiber and allows fatty acids to get into the muscle fiber, and then allows fatty acids to get across the mitochondrial membrane. That fatty acid translocase also increases with endurance training. So that allows you to get a greater amount of fatty acids into the muscle and the mitochondria for fat oxidation if you're aerobically trained. So for this next question, I'm going to identify where all the ATP are produced when you oxidize one molecule of glucose. So the first pathway where you're going to get ATP is through glycolysis. So you have glucose 6-phosphate, and that either came from glucose in the blood coming into the muscle fiber, or it's come from the breakdown of glycolysis. And I'm skipping over a bunch of steps here, but in the end, you're going to get pyruvate. And in the process of glycolysis, there's 2 ATPs that are used in that pathway, and there's 4 ATPs that get produced from that pathway. So in the end, you have a net of 2 ATPs that are produced from the process of glycolysis. So I'm going to do an addition up here for our ATPs from the breakdown of one molecule of glucose. So through glycolysis, you have 2 ATPs that are produced. If you're doing it aerobically, then that pyruvate would go into your mitochondria. So I'm just going to draw kind of a big square here for your mitochondria, so we have lots of room in here. So your pyruvate would enter your mitochondria. It would be converted to acetyl-CoA. And then enter that Krebs cycle. So when it's converted to acetyl-CoA, the key here is that glucose 6-phosphate is a 6-carbon molecule. Your pyruvate is a 3-carbon molecule. So to preserve the carbons, you have 2 pyruvates that are produced. So here you have 2 pyruvates. Your acetyl-CoA is a 2-carbon molecule. So you've lost carbons in this reaction here. So you have 2 CO2s that are produced. 1 for each pyruvate that goes in there. In this reaction, you're producing NADH. So you get 1 NADH that's produced here. And that's eventually going to go to the electron transport chain. And for each NADH that goes to the electron transport chain, you're going to produce 3 ATPs. So there's 2 there and 2 there, 1 for each pyruvate. So when we go up here to add up our ATPs, you're going to get from the PDH reaction, or pyruvate dehydrogenase reaction, you get 2 NADH. When those go to the electron transport chain, they produce 3 ATPs each. So from the pyruvate dehydrogenase reaction, we have 6 ATPs. Now, the Krebs cycle, you're going to have NADH and FADH produced at certain points. So you have NADH You have NADH produced at 3 different points. And you have FADH produced at 1 point. And at 1 point you get ATP or an ATP equivalent formed. So within the Krebs cycle, we're getting 1, 2, 3 NADH. Keep in mind that the Krebs cycle goes around twice because you have 2 acetyl-CoAs. So you're actually getting 6 NADH from the Krebs cycle. So up here I'm going to say Krebs, you get 6 NADH. When they go to the electron transport chain, actually I'm going to draw this, yeah, that's right, 6 NADH, 2 rounds of the Krebs cycle. I'm just going to put a 2 there. 6 NADH. When they go to the electron transport chain, you get 3 ATPs. So that gives you 18 ATPs from the NADH that are produced in the Krebs cycle. Again, 2 rounds of the Krebs cycle, you get 2 FADH. And when that goes to the electron transport chain, it produces about 2 ATPs. So you're getting 4 ATPs from that process. And then within the Krebs cycle itself, you have 1 ATP produced at this step. So it goes around twice, so you end up getting 2 ATPs from that. So now if we add up our ATPs, we're going to end up with 8 plus 18, 26, 30, 32 ATPs. So you probably know that you produce about 36 ATPs from the breakdown of 1 molecule of glucose. So what we're missing here is we're missing 4 ATPs. So the trick here is that within glycolysis itself, higher up in the pathway, you get production of an NADH. Now, if you don't have a lot of mitochondria in your muscle fiber and you end up producing lactate from pyruvate, that NADH will come down here, donate its hydrogen to pyruvate, and then you get formation of lactate. So from pyruvate to lactate, you get addition of a hydrogen onto pyruvate. So if you do have a lot of mitochondria, this NADH ends up going to the mitochondria. But the trick here is that in most instances, it can only it can't pass through the membrane of the mitochondria, so it gives off its hydrogen, and it passes it to FAD on the other side of the mitochondria. So you have kind of a shuttle system here for hydrogens. And you get 2 of these that are produced in glycolysis. You end up with 2 FADH that are produced. These FADH then donate their hydrogen to the electron transport chain. So you have 2 more FADH that come from glycolysis. So you can add that up here. You get 2 FADH times 2 ATPs in the electron transport chain. And that's where you get those missing 4 ATPs. So then you end up with 36 ATPs. Another twist here is that if you're very aerobically trained, then this shuttle system changes slightly, and instead of having 2 FADH produced. On the other side of the mitochondrial membrane, you actually have a different shuttle system that allows 2 NADH to be formed instead of FADH. So that will give you some extra ATPs, and this number would change to 6 ATPs because you get 3 ATP for each NADH, and this would be 38 ATPs. So if you're very aerobically trained and you have this more efficient shuttle system, you can get 38 ATPs out of the oxidation of 1 molecule of glucose instead of 36 ATPs. And that's pretty much a summary of where you get all your ATPs from the complete breakdown of 1 molecule of glucose.